Sounds good. Okay. All right. Welcome, everybody, to another MCRN Colloquium. Today, I have the pleasure of introducing Erik Van Vleck. He's a mathematics professor at the Kansas University in Lawrence, Kansas. Many of you probably know him as he's been involved in MCRN for a long time now and very involved. So it's really exciting to be able to hear from him, and I'm excited because it's a DA talk, so I love those. And with that, excited to hear about dimension reduction for data assimilation, adaptive meshing, and reduced order modeling. So please take it away.
All right, thank you. Thanks for the invitation. Really nice to be here. I see thumbnails of familiar faces, so that's nice. Let me see if I can advance my slides. Okay, so here's a little outline. I'll start out with some background, probably have a little bit too much background on DA, and I'll try to give some motivation and talk about approaches. Talk kind of generally about the need for dimension reduction, in particular in the analysis step. Then I'm going to kind of have two parts to this. One is kind of integrating adaptive meshing into DA, and the other is on basically reduced order modeling for variance of particle filters. And for both of these, I'll try to show some numerical experiments to show kind of the utility of some of the methods we've developed. So here's the kind of general setup I'll work with. I'm going to have a physical model that time steps. So that's this equation one. The state variables at time n would be un, and that's in some state space, finite dimensional state space of dimension nu. We'll assume there's some additive noise that will just, for simplicity, draw from a Gaussian. And we're going to couple this with some observational data. And the observational data is going to be, it's coming from some unknown truth, right? And the way the observations, which are the YNs, are formed is essentially by some observation operator H that takes the true state at time n and produces Yn, and also maybe with a little bit of additive noise here, also from a Gaussian. And to get things started, we'll assume that the kind of U naught is Gaussian centered around some mean U0b with covariance P0b. Okay, so the basic idea behind a lot of data assimilation techniques is basically to apply Bayes' rule. And Bayes' rule basically says that the posterior is proportional to the prior times the likelihood. Okay, so in this equation here, we want to get this posterior distribution, the conditional of U naught with respect to the observed variable y, as the likelihood times the prior. And in the case where the observation operator, say, is linear and the observational noise is Gaussian, we can write down this likelihood as this J of U naught comma y. And if the prior is Gaussian, like we had on the previous slide, we can also write down the prior in kind of this way. Okay, and so what that leads to is, in the case where H is linear, of basically trying to solve this optimization problem. Okay, this prior times the likelihood is the posterior. And there's a couple of ways that we can do this, right? And they're actually kind of equivalent, right? One is we do this optimization. We have this, what I have over on the left here, this J of X at some fixed time tk, right? And equivalently, if we solve that, what we're actually doing is doing what's called a Kalman filter update. And that's what's in the box in the upper right. Now, a way to extend this is to actually process more observations at one time. And that's what 4D var does. The 4D is basically time plus three-dimensional space, so that adds up to 4. And so here we see that we have a lot of sources of nonlinearity. Not only the potential nonlinearity in the observation operator, but here also in the the physical model. Here I'm using M instead of F to denote the evolution of the physical model. Okay, so the one way that people have gotten around this nonlinearity is by introducing ensemble. So in ensemble common filter, there's these NE ensemble members. These are agents trying to go out and figure out what things look like a little bit. So what we do is we advance, we use our F here to advance the forecast for all the ensemble members. We compute a forecast mean, and from that, a sample forecast covariance given by this PF. So the analysis in this case can then be formed by updating the forecast ensembles using the Kalman gain times the innovation. The innovation is yn minus h of this u hat n plus 1i. And we do this for all the ensemble members as well. Okay, so the important variants that are often employed are these square root filters. And what square root filters do is they basically write this Kalman update as a linear combination of what's called the anomaly matrix. So this XF, if you look at the formula up here for the sample covariance, it's just basically, half of these terms here. And one important aspect of this that makes these methods really work is what's called localization. So you can think of localization as basically trying to localize the influence of the observations. Okay, so weather data for New York City might have some impact on Pittsburgh, but probably not nearly as much impact on what's going on in Los Angeles. The other role that localization plays is that because we're calculating a forecast covariance, we can often get spurious correlations in the forecast, and this localization helps to kind of mask those off. Okay, so another approach is more a variational approach going back to this 4D VAR formulation. And so notice that this, has nonlinearity in the H, in the observation operator, but also because the UN is going to be a function of U naught through the evolution of our physical model. So variational equations have the advantage that we can add other terms to the cost function. We can do a full Newton or BFGS or whatever your favorite optimizer is to deal with the full nonlinearity in the problem. And it's kind of what I call interval sequential, where several observations are assimilated simultaneously. And in this way, we're kind of giving all those observations a kind of a similar weight in determining what the U naught is. The big disadvantage is the fact that this is based on kind of a fixed prior covariance. We don't generate very naturally flow-dependent covariances here. And so that's one of the reasons there's been a lot of emphasis on hybrid techniques. Hybrid techniques basically are trying to take the best of both worlds. We have these flow-dependent covariances with the ensemble common filter type techniques, and we have the way to deal with nonlinearity with the variational techniques. Okay, another class of methods that I've been interested in are called particle filters. And particle filters basically take we do a particle update, which is like a forecast, and then we do a weight update, which is basically based on Bayes' theorem. So each of the particles is given a weight. The weights are non-negative. The weights sum to 1, and they tell us something about the kind of posterior distribution without putting structure on it. So it's a very unstructured way to not, you know, and essentially with the Kalman filter techniques, we're using a Gaussian assumption on the posterior. Here, there's no inherent assumption on the posterior. The difficulty is that often a lot of the weight gets concentrated just on a few particles. So important variants of these are the implicit particle filters, equivalent weights, optimal proposal that I'll talk about, particle flow filters, and one challenge is how to do localization for particle filters. Been some nice work, but I think this is still kind of an outstanding problem. Okay, so let me just try to kind of summarize the kind of why it would be really helpful to do some dimension reduction. So if we let NU denote the dimension of the model space, NY the dimension of the observation space, and NE the number of ensemble members or particles, then the computational efficiency, the computational complexity of doing everything we need to do an analysis step is given here. So what I'm really hoping to avoid is something that's got a big multiplier on NU. Typically, NU is the bigger of these three dimensions. And so if we can cut the NU or the NY, then we can make this a lot more efficient. Okay, so particle filters have kind of a similar cost. Another thing I think I've mentioned this is that particle filters, they have this filter degenerate or weight collapse. And so, for example, for the optimal proposal particle filters, the number of ensemble members that the theory suggests we're going to need is this exponential of the dimension of the model space and the dimension of the observation space. And so this really makes it difficult to effectively apply particle filters. So in high dimensional geophysical applications, we'd like basically 20 to 50 ensemble members. And the general rule of thumb that I read somewhere in my readings on this subject is we'd like that the number of ensemble members to be essentially the number of positive plus close to zero Lyapunov exponents. Okay, so here's a little summary of some dimension reduction techniques, right? Some are kind of data-driven, some are model-driven. We know things like nonlinear Galerkin, inertial manifold, center manifold. These are typically nonlinear techniques. Some of the reduced order modeling techniques are linear techniques like all described today, but others, so for example, like Koopman theory, you know, are moving into this kind of nonlinear. There's stochastic models and techniques. Another one is that I'll talk about is this adaptivity. Okay, we can do adaptivity in both space and time, parameterization of microscale processes, and I would be remiss these days to talk about dimension reduction without at least putting the words machine learning in there. So there we go. So here's some recent work. Our work on reduced order modeling really was motivated by the work on AUS, assimilation in the unstable subspace. And here's some recent references on adaptive spatial meshing for DA as well. Okay, so why do we do adaptive spatial meshing? Well, when approximating PDEs, adaptive techniques in space and time allow for solution, for accurate and efficient approximation of solutions. When there's rapid change in solution in both space and time, we'd like to refine our time step or our mesh to better represent the true solution, the actual underlying PDE solution. So for ensemble-based DA techniques, the use of adaptive spatial meshes gives us a number of challenges, but also some really nice opportunities. It requires that we have computational models with basically a very general adaptive discretization, right? So if we did this with finite differences, you know, we're doing a second derivative approximation, but not with the standard 1 minus 2 1 stencil. Yes. Okay. Was there a question? Okay. All right. So we'd like to get quality ensemble members supported on time evolving meshes and combine these, you know, meshes that support the ensembles with meshes that support the observations in their locations. Okay. And there's a desire for both accuracy and efficiency to minimize interpolation and extrapolation. And moving forward, what we'd like to do is kind of almost anticipate some behaviors by putting in meshes that will support things that may be happening, but without kind of putting a mesh out there we may not be able to resolve. Okay, so there's a number of existing techniques. I'll kind of split them up into what I would call kind of approaches that use augmented variables. In this case, we'd assimilate both the dependent variable of the PDEU and the spatial variable X and try to find kind of some common ensemble meshes. There's a number of common mesh approaches, and what I'll talk about today will fall under that umbrella as well. And so our challenge is to design higher space dimensional adaptive meshes in 2 and 3 space dimensions to support analysis and forecast. So our first published work on this was based on I'll use these two terms synonymously, metric tensor and mesh density function. So we did this in RD. So these mesh density functions are locally for a fixed time and a fixed point in space. They're D by D symmetric positive definite matrices. So they basically define ellipses pointwise. And so we're going to use these in a variational framework to design meshes that are uniform with respect to this mesh density function. Okay. So, and what we're going to do is we're going to combine mesh density functions to bring in different aspects that should impact the mesh we're going to use. And we're going to combine those and then generate a mesh instead of trying to combine meshes for different things more directly. Okay, so here's a little schematic. In our earlier work, what we did is we took the approach that I'm labeling with an A. So for each ensemble member, they had their own independent forecast mesh. And then before we did the analysis, we kind of averaged that mesh to find a mesh that was pretty good for all the ensemble members and also took into account the location of the observations so we could move mesh points near where observations are occurring. Okay, so we had an independent mesh for each ensemble forecast and a common mesh for analysis. In B, what we're doing, and this is what I'll describe today a little bit is what's in B, we took a subset of our full ensemble and had them go out and kind of sample what the behavior in the next forecast and analysis was going to look like. And so we take this small ensemble and create from it these mesh density functions that we combine. We also factor in what we need to do to support the observations. We put that in with the forecast mesh as well. So in the scenario B, we have a common mesh for all ensemble members that's used both for the forecast and then for the analysis. After the analysis, we send out our small ensemble again to learn about what the next common look-ahead mesh should look like for the next forecast and analysis cycle. Okay, so we're using variational mesh adaptation where we think of the U, the dependent variable, the PDE, as a function of X and T, but now we're saying, well, hey, X is going to be a function of T as well. So this gives us an extra term, this term in equation 10, this kind of advective term here, because the mesh is moving. So we're solving a slightly different PDE because of this advective term, and we're going to couple that for an equation that moves the mesh. Okay, so that's this equation 11. So 11 comes from, we're basically embedding the gradient of some meshing functional, this IH of X of U, into a gradient system. So we're doing a kind of a gradient descent method. Obviously, other techniques, predictor corrector techniques, continuation methods could be used to do this. But this kind of gives us a nice common framework where we now have this coupled system of differential equations to solve. Okay, so we couple these equations, and one thing we're going to do, we're going to use what I would call a quasi-Lagrangian approach. So instead of the G that controls the mesh movement depending on U, it's going to depend upon a mesh density function or metric tensor. Okay, so this allows us in a DA context to bring in not just the ensembles, a mesh that's good for the ensembles, but a way to focus points near observations, to take into account other things, other features that we think may be important for getting high quality DA results. So this mesh density, Hessian-based mesh density function, this is a widely used one in the numerical PDE meshing literature. It's based on a recovered Hessian it depends on having a scalar field U, okay, and we get this. This is kind of based on minimizing an L2 interpolation error. An ad hoc mesh density function we've employed to focus mesh points near observation locations is the following. This is just a bunch of Gaussian bumps that are centered on the observation locations. And finally, here in equation 13 is another mesh density function that we derive for these non-local observation operators. So these come from this kind of convolution type interval. And this is actually very similar to the Hessian-based approach for the ensemble solutions. Okay, so what we do is we're trying to find this mesh density function that's going to do a good job. And we have several sources that are going to feed into this. The two primary ones being the good solution of the ensemble forecasts, and then factoring in the observations. There may be other features that we want to incorporate as well, and I'll talk about those a little bit more at the end of the talk. So the easy place to understand these mesh density functions is in one space dimension. So in one space dimension, these are basically just positive numbers that are inversely proportional to the mesh spacing. Okay, so when we do this intersection, metric tensor intersection, it's a max operation. So if I take two metric tensors that are supported on some reference mesh, and we take their intersection, what we get is the maximum of the local values of the metric tensor. And in higher dimensions, what we're doing is basically kind of intersecting these ellipses. So this is actually showing basically we have these two ellipses here. we find the intersection. And this picture actually corresponds to what happens to the mesh, as opposed to what happens to the mesh density function. So this combining of metric tensors is very cheap. It's not expensive at all. It's a lot of D by D linear algebra. I think we have to do a couple of really small matrix factorizations, but D is the space dimension of our PDE. So typically that's going to be 1, 2, or 3. It's all very local, so highly parallel. All right, so here's an example. And let me just try to show this. This is from an example for a 2D inviscid burgers. So in the upper left, we have the observational mesh, and the red dots are the support of the observations. So the observations are supported on these 2 quarter circles. Okay, and here in the upper right is the ensemble mean. Okay, and then if we go down to the lower right, we see the kind of mesh that supports those ensemble members. And then if we combine those using the metric tensor intersection, we get something that still has fine mesh near where there's rapid change in the solution of the Burgers equation, but also we get points, we get much more finer mesh. We get a finer mesh near the location of the observations. Okay, so we're trying to kind of balance these two things, the accurate solution of the ensemble solutions and the location of the observations. Okay, so what we are doing, and this slide is really just to kind of illustrate what could be done in some, so if you had a different meshing system, what kind of capabilities would one need? Okay, so this is kind of abstractly what I think one needs in order to do something like what I'm describing. So we need a way to take U, supported on an old mesh, and some mesh, and get a metric tensor or mesh density function out of it. A way to evolve the mesh from an old mesh to a new mesh, given this updated metric tensor M, and then we're kind of regularized with respect to some reference mesh. And oftentimes the reference mesh is just a uniform mesh. Okay, so we can recursively form metric tensors by just kind of updating using the metric tensor intersection. So we can try to form metric tensors that are good over an interval of time. Okay, and then once we've done that, we could then update our mesh to go from a mesh that was good at TJ to one that's going to be good at TJ plus 1. Okay, and so here's a couple of ways that we've accumulated some of these meshes. We call LAH is short for look ahead. Okay, so the first way in equation 15, right, we get this. So delta T, think of that as the time between observations. So we're getting for the ith ensemble member, we're getting a mesh density function for this interval T to T plus delta T. We're going to intersect that with some metric tensor for the observations at this end time. Or in 16, what we do is we kind of, 16 is better seems to work better when we have moving observations. And so this way we kind of anticipate the movement because we're updating the observational mesh density function as we go along. And then once we found this look ahead mesh, then we advance the solution. And this is what's going to support our forecasts and our forecast ensemble and the analysis over the next forecast and analysis cycle. Okay. So here's kind of a schematic of what we're trying to do, right? So these are just traveling wave, kind of snapshots of a traveling wave solution. Okay. And so at different times, we're moving from, say, left to right. And as we do this, if we're doing a good job with the meshing, then what happens is the mesh is concentrated where the solution is varying rapidly. And so this requires us to move the mesh, update the solution to the new mesh, et cetera. And so instead, in the bottom plot here, what we've done is we found this kind of look-ahead mesh that combines these meshes here. So we have one mesh that's maybe not as good as any of the individual, but it's pretty good overall. And we're able to just use our adaptive discretization and just solve over a longer time interval without having to update the mesh and the solution on the mesh. Okay, so this is a little bit of an illustration. This is a 2D Inviscid-Burgers equation where the time between observations is 1. What I'm showing here is how the RMSE reacts to the number of ensemble members we use to make the look-ahead mesh. So when the small ensemble size is 1, what we actually use is, as an initial condition, we use the ensemble mean. Okay, and then we sample that as we move forward in time and accumulate a metric tensor for this interval over this unit length of time. Okay, and then we're going to compare with using 2 randomly selected ensemble members, and then 4 and also 8. And we get some improvement, right? As the number of ensemble members is increasing, our RMSE is getting lower, but we kind of hit diminishing returns when we're at about 4. I mean, the result for 8 is not much better. Here for this example, we're using these kind of moving observations. The ones in green are the old ones. The ones in red are the new ones. Here's the mesh that we have that supports these observations. This mesh, notice, takes into account the form of the ensemble solutions as well as the location of the observations. Okay. We also find that, so what we're using here to time step is a strongly stability preserving embedded Runge-Kutta method. So it's a 4-3 pair. Okay, we're discretizing in time. This is an inviscid problem. We're doing a discontinuous Galerkin approximation in space, and this embedded pair Runge-Kutta method in time. And what I've shown here are the time steps for all the ensemble members. And the nice thing about this, and this is another area where I think we could get some more out of this, the time steps are all very similar. So, I mean, in these experiments, the ensemble members time step independently. But these results suggest that perhaps a scheme where we have time stepping that is done, the same times for all the ensemble members, which would again add to some vectorization and parallelization. This is another example. Here is a 2D shallow water. So this is relatively standard. We've got the 2 velocity variables and the height variables. There's several constants in here. We've non-dimensionalized scaled space, time, and dependent variables. This is a 3-component problem. We put all 3 components on the same mesh. And the way we do that is we take a metric tensor for the new height, and then a metric tensor for this combination that's related to the way we rescaled everything. And then we combine those two, and that's the metric tensor that we use to generate the mesh for all 3 components. Here are some of the values, the covariances, how they're set, the number. We're just going to use pointwise observations on a uniform grid. And below here, these are some snapshots of over the time interval we're going to do this simulation. Okay, and we get nice results here that you know we get improved results with more observations. We can take a relatively large observational time scale, and we're using a small ensemble of just 4 to get these results. So this small ensemble really, those forecasts really don't add much to the calculations. All right, so that was part 1, and I'm going to see how far I can get for part 2. So this has been something that I've been interested in for several years now. Basically, using reduced dimensional surrogate models to do dimension reduction to get some better outcomes from particle filters. So the general idea is we're interested in problems with 2 or more high probability outcomes. These are often associated with events that are localized in space and time. You know, it might happen for, you know, like with a hurricane, we might care for a couple weeks. You know, we'll probably care along the eastern seaboard. And we want to know things like, will Hurricane Sandy stay out to sea or head inland? And if so, where and when? So with these multimodal posterior distributions, you know, there's the main possibilities are some kind of Gaussian mixture model, or try to get something more out of these particle filters. And so basically what we're doing is we're doing something that's similar to kind of a Petrov-Galerkin approximation of our physical model. Okay, that's in here in 18 and 19. Okay, these are reduced dimensional models. And then something that we've really worked a lot on is doing reduced dimensional data models. Okay, and so a couple of recent works, and probably unsurprisingly, these both came out of associations with MCRN. The first problem here, we use reduced dimensional surrogate models that we obtain from short forecast sliding window POD. This is kind of not the standard approach when doing these reduced order models. Usually we're trying to find kind of global coordinates, and these are very local coordinates. And so this is kind of a way to get around the nonlinearity by doing something that's a little more kind of time dependent. Okay, and then the second paper came out earlier this year, and it's on combining a particle filter with ensemble common filter. So we combine a low dimensional surrogate model for the particle filter, and then update the remainder using an ensemble common filter. Okay, so the particle filter we've been using a lot is what's called the optimal proposal particle filter. I'm now using L for the number of particles, M for the model dimension, and D for the data dimension. So with the optimal proposal, the Kalman update the particle update is similar to a common update, but with the model error covariance proposed in place of the prior error covariance. Okay. And so for this, we use the projected physical model and the original data model, the full data. For the weight update, we basically we have a likelihood that's associated with the particle update that uses both the projected physical and data models. So the new weights are proportional to the likelihood times the old weights. And if we start to see filter collapse, we resample. Okay, so this is really a big discontinuous change, and we'd really like to avoid resampling. So this is one of the criteria that we report on to show how well our methods might be performing. Okay, so traditional ROM techniques like POD, DMD, they seek global in time coordinates for the dominant dynamics. Okay, so here are this couple of SIME review articles by Benner and Brunton. So the idea is you have the traditional approach is you have a large snapshot window. Okay, and so we're going to find these kind of global coordinates. So the idea we had was instead try to find local coordinates, local in time. So we change the coordinates often. So one advantage is that we can employ short, accurate forecasts. This is computationally efficient, and we will really only require good local coordinates with our setup. So this is one of the nice advantages. And so let me see. So what we have, this is the technique we use. So the POD is based on proper orthogonal. It's based on the dominant left singular vectors of a matrix of snapshots. So we sample at fixed times, these TIs. TS is the number of samples. Tau D is the time between observations. And we apply our POD to go up to, for this snapshot matrix X that has solutions for times TI up to TI plus 2. And we use this we only apply this for T in the first half of this snapshot interval. To get the projections for the data model, we apply POD to H, our observation operator applied to the snapshot matrix. We could apply it, for example, directly to snapshots of observations themselves. Okay, and the typical thing is we set some tolerance and we determine what the rank, how many columns we're going to use based on having some percentage, of the kind of the singular value mass. Another thing that we've added into this is what I'll call sparse mode selection. Okay, so typically in these reduced order modeling techniques, we kind of think of these coordinates or modes or directions as being ordered from most significant to least significant. And so what a sparse mode selection does is allows us to kind of not go from the top dominant one down as far as we need, but to pick out from the middle of these columns the modes we're trying to use. Okay, so this slide, what we have is we're going to vary. The main thing we're going to vary here is the number of snapshots. So this is a Lorenz 96 example. In the first half of the time, we're going to have F equal 8, which is the nice hard problem. F equal 3 is in the right of the interval. And we're going to take a 400-dimensional model. We're going to use H to be the identity. So we're going to observe all the variables. The time between observations is 1, and here's the way we set some of the covariances. We're going to use 20 particles, and we have some tolerances. And so the thing we set up here is basically this little sentence here before the two figures. If the snapshot M is if the snapshot X is full rank, then we get no projection error. So if we take the rank R to be 2 tau S, which is the full rank, then all the snapshots are going to be just reproduced. Okay, and so we see some nice results here. We start out with 500. The RMSE is a bit above our target line, but by the time we get down to 20, it's well below the target line, even in the case of F equal 8. Okay, we don't resample very often. There's some resampling, but it's for these good cases, it's down into the single digits in terms of percentages. And here in this bottom figure are what our reduced dimensions were. MQ is the reduced model dimension, and DQ is the reduced data dimension. And you can see the reduced data dimension is down there, basically 1 or 2. Okay, and so here is another plot, another set of plots, where what we're doing now is we're using some sparse observations, and we're also we're varying the time between observations at both 1 and 0.1. So I down arrow 10, that's denoting observing every 10th variable. I down arrow 5 is every 5th variable. Okay, and so we see some really pretty good results for H equal I down arrow 5 and tau D equal 1. The both of those where we do every 5th are pretty good, and we get pretty good results for H equal down arrow 10 and tau D equal 0.1 as well. Resampling is really low. We don't have to resample. And yeah, okay. So the last thing I have to talk about, and I probably barely have enough time, is this work on decomposing Gaussian likelihoods so that we can split up the problem into a problem that we can apply, say, a particle filter, a low dimensional particle filter, and then have a remainder term. And the simplest case is we have these two projections, and we're going to try to decompose the likelihood. And when we do this, we're doing this through basically a little linear algebra result on some block symmetric positive definite matrices. So we can write the likelihood as the product of these two likelihoods. And here's the data we use in Y1 we do the projected data with U1, H1 similarly, and that's its covariance. And then Y2 is Y and H2 is H, the original Y and the original H. And then R2 is what we've found, and it has this generalized inverse like this. The plot here is a little schematic. We're reproducing the whole inverse of R, but not necessarily reproducing all of R. And so it's the R inverse that we use in the likelihood, and the R that we're really using for the sampling. Okay, we applied this to what's been coined as a storm tracker L96. So the original L96 has this linear dissipation term. Bishop et al., what they did was they basically had this dissipation term change with space, And our storm track model, what we did was we had it change with both space and time. For the forcing, for the forecast model, we use f equal 5. So we're introducing a structural error there because we're using f equal 8 as the truth. That's what we compare to when we compare the RMSEs, and it's also f equals 8 is what we use to generate the observations. So we do a projected optimal proposal particle filter on a one-dimensional subspace corresponding to the largest Lyapunov exponent. We use kind of a continuous resampling technique to impose equal weights. And for the remainder, we update with an ENKF. We compare with just a full-blown OPPF, an ensemble transform Kalman filter, and a stochastic ENKF. The plots here, the first is the one that says grid point, right? This is kind of showing the solution behavior. So we get the more kind of complex behavior in kind of a meandering river that kind of periodically goes back and forth in space and time. And so here's kind of the RMSE results. We get nice results for this PF ENKF that we've developed here. We see some reasonable behavior from the rank histogram. Our PF ENKF, it still has a spike at 1, but it's a little more flat and doesn't have a spike near 0, which is generally good. So with that, I got a couple slides to finish up here. Future work. We're starting to focus on hybrid ensemble variational methods. I mean, I think both of these, both using reduced order modeling and adaptive meshing, I think have good potential here. The fact that we're using short forecasts to do our POD means that we may be able to match like the 4D VAR window when doing that. And we also are hoping to extend this look ahead idea to see if we can get what kind of meshes we can get over a full 4D VAR window. And for the ROM techniques, we're focusing now a little bit more on using projections to do local analysis. It's pretty easy, I mean, basically local analysis like domain localization is done with kind of like basically trivial projections, 0i, 0 kind of generators. And we're going to see if some of these reduced order modeling techniques can give us something there. Maybe we'll do fewer updates. And then kind of adaptive ways we can update the number of snapshots and the time at which we resample the snapshot matrix. I mean, do we see the accuracy fall off? So do we need more snapshots, or do we need to resample? We're continuing to develop mesh density functions for features like flow features, sensitivities, being able to focus on some place in space and time, and also on updating covariance matrices that might be supported initially in our problem formulation on a reference mesh, but then we're gonna use some version of them on an adaptive, on an updated mesh. So some support for this from NSF, at least previously, and currently from ONR. And here's some related publications and a list of my collaborators through which none of this would have been possible. So thank you very much.
Okay. Yes, let's all thank Erik for the very interesting talk. It was really nice. I guess we have some time for questions. I could open it up if anybody has a question, please feel free to ask.